So thank you, Massimo, for your kind introduction, and it's really an honor to be here in this very prominent place for the University of Florence, and I'm really honored to transmit you a scientific story, because it would be not a strictly scientific contribution, a discussion, but it will be a mineralogical tale that I want to introduce you. And I believe that you can see that this communication deals with natural quasicrystals, but it is actually a better title, something like this, for a mineralogical tale, because you see impossible cute, because in this communication there will be 3 levels of impossibility. Well, the first level is surely that it was only impossible to think that this kind of material could exist in nature. And the second level of impossibility was that this kind of material was exactly in the mineralogical collection of the person who was looking for them. And the third level of impossibility was to think the origin of this kind of material. So you can try to think of the most crazy idea for this kind of material. Well, they came from the outer space. So there are 3 levels of impossibility that I try to transmit you today. So, but I promised you a mineralogical tale, so the best thing is to introduce you the characters of the story. Well, the first is Paul Steinert. Paul is Albert Einstein Professor at the Princeton University, Department of Physics. Well, he's very famous as cosmologist, because he's one of the architects of the inflationary model of the universe, together with Alan Guth and other person in MIT. So his vision of the different tails of the universe, so beyond the Big Bang. So it is, I cannot understand anything about this, but it is very important in condensed matter physics, as you know, because he, together with Dov Levine, today at Technion, together with Dennis Sheckman, introduced the concept of quasicrystals in a theoretical way. So the solid matter, so you know very well these kind of materials. The other person of the team is Nan Yao. Nan is the director of the PRISM, the amazing center of the Princeton University, and is an incredible guy able to manipulate I would say nanomaterials. So he is very famous in the United States because he introduced 2 important books recently and tried to focus together the focused ion beam technique and transmission electron microscopy applied to nanotechnologies. So the third person of the theme is Peter. Peter is the youngest guy of the group. He's a researcher, Department of Physics, Harvard University. He belongs to an important group of Harvard, the group of Professor Bates. Probably most of you know him. And they work on colloids and the gelation of particles. So Peter came to the media attention to this paper on Nature on the gelation of particles in 2008. Well, now we have the geologist, so the most important person, of course, and the first is Lincoln Hollister. Link is retired professor, Department of Geoscience, Princeton, and is really, believe me, a giant in the geology, because he contributed to the important understanding of very important ABC basic principles of geology, like compositional zoning in minerals, in fluid inclusion in metamorphic rocks. And just a remark, he was the principal investigator of the lunar program in a very hot period for the United States. So the man on the moon, and so Link was able to distribute the different samples from different Apollo missions to the different American labs. Now we have Glenn McPherson. Glenn is the curator of the Division of Meteorites, so for the most important natural history museum in the world. So we're talking about the Smithsonian Institution, Washington. And is considered, I would say that from the mineralogical and geological community, as one of the leading experts in the world in meteorites. And actually, I would say that more exactly in carbonaceous chondrites. So we are talking of the oldest extraterrestrial objects, about 5 billion years old. Okay? So it did other achievements of Glenn. So the last person is John Ayler. John is Robert Sharp Professor of Geology and Geochemistry at the California Institute of Technology. And so he's an experimentalist working with oxygen isotopes, I would say isotope measurements of light elements to reconstruct the origin of the life and also the potential habitability of life in other planets. Well, so now you know the characters of the story. So I would like to introduce you what you can find in all the basic textbooks of mineralogy. So this is the definition of mineral, defined from approximately 200 history. 200 years history of this discipline. So a mineral is a naturally occurring homogeneous inorganic solid substance having a definite chemical composition and a characteristic crystallized structure in which the position of the atoms are arranged in a periodic lattice of points repeated in the 3 dimensions, and where each unit cell has a pattern identical to that as around. So this is the basic text definition of mineral. If you try to make a summary of this definition and to say what are minerals, we can say that they are characterized by a long-range periodic order. So this is a sodium chloride structure, of course. So this means that they are a periodic long-range order. So what about quasicrystals? Well, so quasicrystals, the pattern is of course quasi-periodic. So this means that the local arrangement of atoms is fixed at the regular as the best crystalline materials, but is so as a different configuration with respect to that that's around. So if we try to make something like a short sentence also for quasicrystals, we can say that they are characterized by a long-range aperiodic order. So what does mean long-range aperiodic? So the fact to have a long-range order means that if I carried out an X-ray diffraction study, I will see sharp and strong diffraction peaks as the best crystalline material. But the fact to have no 3-dimensional translation periodicity means that I can see non-crystallographic symmetry axes. Well, so what about non-crystallographic symmetry axes? So I make an example very, very, very familiar for you probably. But what about the crystallographic symmetry axis? So imagine that you have covered your floor or your bathroom, for example, with different tiles. So you have to cover your floor without leaving gaps, bags, or holes. So you can have something like this. So you can have identical tiles, rectangular, 2-fold symmetry, square, 4-fold symmetry, or triangular or hexagonal tiles, so 3-fold and 6-fold axes respectively. So you have crystallographic symmetry axis 1, 2, 3, 4, 6. What about 5? Well, this is what happens if you try to tile your floor with pentagonal tiles. So you will see that you have gaps, cracks, and holes. So this pentagonal is governed by 5-fold symmetry, which is a non-crystallographic symmetry axis. Well, so in other words, what are these kind of materials? So what are quasicrystals? So, of course, when Paul coined the name, quasicrystals is the short for quasi-periodic materials, quasi-periodic crystals. So they are solid with diffraction patterns composed of Bragg peaks, so the sharp with the Bragg peaks, but with symmetry forbidden to crystals. So 5-fold symmetry in 2 dimensions, or icosahedral symmetry in 3 dimensions. Well, so icosahedral. So it is a not familiar term, but we know very well what is an icosahedron because it is the symmetry of a soccer ball. So it is very famous in Italy. So an icosahedron is pumped to a sphere in this way, but you can see 3-fold, 5-fold, and 2-fold symmetry axis. So this is an icosahedron. Well, so to make the story more fascinating, so in 1974, the mathematician and cosmologist famous Roger Penrose discovered this remarkable pattern, constructed of 2 tiles, the purple and the green tile. But this tile was very, very important because, as you can see, it shows a 5-fold symmetry. Well, later it was shown actually that the tiles repeat after an irrational number, so which is the golden ratio. What is important is that Levin and Steiner, 1984, pay attention to the years, showed that any symmetry was possible in 2 and 3 dimensions using other quasi-periodic ratios, not only the golden ratio. So you can see that we can obtain amazing image, something like this, 7-fold symmetry, or 11-fold symmetry, or something like this, 17-fold symmetry. You can see that the increase of the tiles, it is a very complex image, but the results is amazing, okay? But anyway, these are all fascinating considerations. So, but there are something like philosophical considerations. So we are scientists, so we need an experimental proof to believe in. But as it happens, the same here, 1984. Dennis Sheckman, Ilan Bless, Dennis Grasses, and John Kahn, 1984, overcooling and icosahedral feathery grains of aluminum manganese found experimental evidence. So you can see here this actually very describable diffraction. So you can see here the 5-fold symmetry, okay, in this place. Well, Danny was a visiting professor at NIST in Washington in that period, and he obtained this experimental imaging 2 years before, in 1982. And he was there under the supervision of the eminent U.S. metallurgist John Kahn. Well, this was the reaction of John when I see for the first time the Danish-Sheckman experiments. So go away. These are twins, so intergrown or periodic structures, and that's not very answering. So this is something like the view of Linus Pauling, okay? Well, fortunately, John Kent changed his mind relatively soon. There are a lot of mysteries in this 2 years period. Anyway, it is not the case to discuss them, and so in 1984 appeared one of the most important crystallographic articles published in Physical Review Letters in 1984, Sheckman and collaborators, the first experimental proof of the existence of this kind of material. Well, for this reason, you know much better than me that then it took the Nobel Prize some months ago in chemistry for its discovery of quasicrystals. Well, so 1984, the field has blossomed. You can have really several examples of quasicrystals with different chemistry. So you can see, for instance, this amazing picture of icosahedral flowers of aluminum manganese, so the same material studied by Danny. Or you can have decagonal crystals of aluminum nickel cobalt, or for instance, icosahedral grains of aluminum lithium copper, the perfect icosahedral grain of zinc magnesium holmium, okay, so very strange composition, and decagonal grains of aluminum manganese palladium. Okay, so now you know who are the characters of the story, and you know what are quasicrystals. Okay, you know already what they are, but anyway. So why they are so important? So this is the explanation I give to geology. So sorry for this, but the fact that these materials there's no translation periodicity, is a quasi-periodicity, means that it has obviously a consequence of the physical properties. And especially anomalous behavior of metals composing them. So try to make an example, a very, very simple example. Take copper. Okay, copper, if you take copper alone and increase in temperature, of course, you increase the electrical conductivity of this kind of metals. But if you take copper inside an alloy to form a quasicrystals, and increase in temperature, it decreases the electrical conductivity and increases resistivity. In the same way, if you take copper alone, it is very malleable and ductile, so you can work with wires, for instance. But if you take copper inside an alloy to form quasicrystals, it becomes rigid and slippery. This justified this application of quasicrystals, of copper quasicrystals, as alternative of Teflon. But it is not a virtual application. For instance, in 1991, the Cybernox, an American company, produced a battery of paints which are something like the tin pieces is of quasicrystals and not of Teflon. Okay, so there are a lot of application of these kind of materials. Well, so now we know why they are so important. The most important question is this: why to search them in nature? There are several motivations, of course, but for instance, the first is important, of course, for me. It opened a new chapter in the study of mineralogy because it would alter forever the study of this discipline, because it would expand the catalog of materials formed by nature. It would push back the age of the oldest quasicrystals by orders of magnitude. Take in mind that the Danish-Sheckman made the oldest quasicrystals we know is the Danish-Sheckman, so 1982, 30 years. Finding something in nature would mean millions of years, okay? So to impact our view on how difficult it is to form this kind of material, and it would be important for the quasicrystal stability after extraordinary annealing times, and probably the most important for me, may suggest new geological or extraterrestrial processes. Okay, so now we are ready to understand in which way the story went, because 7 years ago I was reading this paper published in Physical Review Letters. You can see that 3 of these authors are the same person who worked with me in the search of natural materials, Peter, Paul, and Nan. So this was a very ambitious paper published. It was the first paper of the senior PhD thesis of Peter in Harvard. It was ambitious because they wanted to try some statistical figures of merit able to identify, on the basis of the X-ray powder diffraction, new potential promising quasicrystal candidates. So they were analyzing in a statistical way all the diffraction pattern present in the JGP database. So we're talking about 80,000, okay, of diffraction patterns. What was important for me was this table in this paper. Because you can see these are the promising quasicrystal candidates divided for the 3 different categories of quasicrystals, so simple icosahedral and so on. We are not interested in this differentiation. What is important is that there are 3 minerals as promising candidates. So I was shocked to see that. Actashite, tantalite, and gratonite. So they are considered with these statistical figures of merit as potential quasicrystal candidates. So I finished the article and I found a curious sentence at the end. We are interested in collaborating in exploring these candidates whose interest can conduct us. Well, so I immediately went in the mineralogical collection of the Florence Museum and I saw if I had these samples, okay, samples of actashite tantalite, and as soon as I realized that I had the samples, I decided to contact them. Well, the reaction I had with Paul and Peter was was amazing. They were very, very happy to start this collaboration. Anyway, my work was a bit harder with respect to that prospecting in the paper because I had to analyze 6 minerals and not only 3. And here are divided into the different categories, and this is the position in the ranking of the potential quasicrystal candidates. So here, for instance, actashite is very, very promising on the basis of these figures of merit. So what I had to do? I had to do a single crystal X-ray investigation to see the eventual forbidden symmetry and an electron microscope analysis to verify if these minerals could be really the name reported in the label of the museum sample. So it's not interest, of course. What is interesting, all the samples did not show either crystallographic forbidden symmetry or evidence in commensurability. Well, so I was very happy that way because I tried to tell to Paul that the only paper we could write would be that probably their figures of merit did not work so well as they believe. And so they were very happy to publish something like this. So our collaboration stuck for a bit. And so some weeks later, I tried to find out another way to find out the natural quasicrystals. So something different, so not so complex to be understood. So I put in front of me something like this. This is a list of synthetic compounds proven to be with the forbidden symmetry in the lab. So they are quasicrystals, synthetic quasicrystals. Okay? So what I realized, you can see it in 5 seconds. So I tried to find a link among all these samples. And I realized that all of them show metallic aluminum inside and very often metallic and copper. Probably so the most clever idea would have been to find out if in the nature exists something like this. So searching for aluminum copper alloys in nature. So there are some minerals described in the mineralogical database with this kind of composition. So I tried immediately to find out in the mineralogical database there are minerals with this composition. And my search was 5 minutes because yes, there exist 2 minerals with this very exotic name, so typical for mineralogists anyway. This is catechite from the Katilka River and cupalite for copper and aluminum. And they are copper aluminides with minor zinc inside, okay? So they were described, try to remember such name, by Razin and co-authors in 1985. So what we can say about this description? Yeah, these kind of minerals were found in metal placers. So what does mean? Means that there are rivers coming down from the Koryak Mountains. We are talking of a remote region in the north part of the Chukotka. So we are talking of the north part of the Kamchatka Peninsula. Probably you know him from the Risk, okay? Yes. So we are talking of that region. And they were found as metal places, so metal nugget. So we are talking of poor metal, okay? Poor metal. This is important. So what I have to do in this period, with the differentiation of the Soviet Union in that period, a lot of persons try to find out platinum nuggets, gold nuggets in these regions and try to sell to the Western people. Anyway, I tried to find out if the mineralogical sample, one of these samples was actually present in the mineralogical collection of the University of Florence. And I have to say that I was lucky. But you can think what you want in your head, but anyway, this was one sample present in the Florence collection. So he entered in the museum in 1919. You can see that it is cataloged coming from the Katurka River, Koryak Mountains, Russia, so the same location than the Russian occurrence. Okay, pay attention. So this is the size of the samples. So it is in this red dash of circle. So we are talking of a 3 millimeter sample, okay? So these are 5 cents. Fortunately, I took a picture, an high resolution picture of the sample before 2 slides for experiment. So this is a very important image because you can see that it is not a metal placer, and not a metallic nugget, okay? But it is something like an aggregation of different minerals. So in geology, it means a rock, an aggregation of different minerals, okay? So you can see these blackish, grayish materials, which is catricite and cupellite intergrown together, and you have this whitish material, which are rock-forming minerals with very exotic names, okay? It's not important for... So they are silicates, okay? And oxide. Well, so a $1 million question. So how to be sure that these Florence samples in the museum was exactly from Kamchatka? It was a really, really important question because, pay attention, this is a question all the person working with museum samples had to do, but in this case was very important because we deal with an historical sample containing the first natural quasicrystal. So we had to trace back the origin of this material. And believe me, it is not a joke. We had to deal in this period with secret diaries. We have to work as secret agents. Believe me, it's true. And we deal with secret lunar samples served in the Russian Soviet Union stocks, and then we finished with bears. So it is a long story, about 1 year, but believe me, it is really worthy of the detective novel of a book. Anyway, just to make the story very, very short, we took the paper of Razin and co-authors in 1985, okay, you remember? And so this is really, believe me, here is written V.V. Kryachko. So this was the person who physically collected the samples and then gave them to Razin and the others to make the new mineral catricite and cupellite. But the person who physically collected the samples was Valery Kryachko, okay? So we had to find Valery, and after several agency work, we were able to find Valery. And so, since he is the hero of the story, I have to show him. This is Valery. This is Valery, 1979, Katirka River. So we are talking about Chukotka. So try to imagine a thing. So Valery had the Florence sample in his hands in 1979. So 3 years before Dendane made the experimental proof of the first quasicrystal in the lab. So this is an amazing coincidence. Anyway, thanks to Valery, which is a very perfect geologist with very careful notes and very careful geographic coordinates, we were able to locate exactly the place for the Florence sample. So this is the Kamchatka Peninsula, this is the Chukotka region, the Bering Sea, Alaska, okay? So we are talking of one of the most remote regions of the Russia. And so this is a blow-up, and another one with latitude and longitude. Very, very important if you try to plan a scientific expedition in the field. Well, so what about the Florence samples? Just very quickly. So we tried to slice, okay? Let's slice the Florence samples, the 3 millimeter size samples, to see the internal structure. It was studied by scanning electron microscopy and electron microprobe. And you can see that 2 levels of gray, so they are catricite and cupellite intergrown together. And you can see all these points, yellow and red points, corresponds to catricite and cupellite respectively, but it is not important. What I want is that you focus your attention on these 2 grains. We are talking of a 60 microns grains with the yellow points inside. Well, at the electron microprobe, this was the results of 18 analyses, aluminum, copper, and iron. Well, this was the chemical composition when normalized to 100 atoms. Well, when I saw this kind of chemical composition, I was really shocked because I jumped on my chair because this corresponds exactly to a synthetic quasicrystals proved to be forbidden symmetry in the lab. So I was already sure to have found the first natural quasicrystal. What I have to do, in addition, I could try to extract the crystals by hand, picking, and try to obtain an X-ray diffraction investigation. So I was able to extract the grains. It was a very hard work, believe me. Anyway, when I extract the grains, I immediately run to the CRYST, so the lab in other buildings, to make an X-ray diffraction investigation. So, well, the results were very disappointing at the beginning, because you can see that the crystal does not diffract a single crystal. So you can see not single crystals, single spots. When you have diffraction cones. Anyway, it is not important because we can easily convert in a conventional diffraction pattern, so something like this, so you can see the sharp diffraction peaks. And what is important is that if you try to plot the data for the natural crystal, this red triangle, these are the two figures of merit introduced by the American guys. You can see that this natural material fall in the area of synthetic quasicrystals probed with forbidden symmetry in the lab, and very, very far from the huge amount of 80,000 diffraction pattern of crystalline materials. So I was sure at this point to have found the first natural quasicrystal. Well, so I decided to recontact the American guys, and Paul told me, well, fly down, because you have not found anything for the moment, because you need the overwhelming evidence. If you want to say, if you want to make something like this claim, we have to have overwhelming evidence of quasicrystallinity. So you need a transmission electron microscopy showing the five-fold symmetry. Well, so for this reason, I decided to send the crystals to them in Princeton, and the crystals arrived in November 2008. And believe me, the crystals are at the end of these arrows on the glass roads, are not visible, but they are there, fortunately. And at this point, none did an excellent work. You remember that the crystals were attached to glass rods were something like powdery aggregates. So when Nan took one of these, put in acetone, and the grain disgloed in several micrograins, well, he was able to select one of these grains, 1 micron in size, and this grain showed thin edges able to give electron diffraction pattern. Well, it was the beginning of 2009 when Paul sent to me this email, Quasi Happy New Year. Well, I see that you immediately realize, so they were come back from the lab and they found the overwhelming evidence we were looking for, they're already found. Okay, so it was very excited, Paul, because it is a theorist, so he works something like an experimentalist. Anyway, some hours later, they sent to me something like this, so you can see that they were able not only to find the five-fold symmetry axis, but also the two- and the three-fold symmetry axis, so to characterize all the symmetry of the icosahedron. Well, some weeks later, they sent to me also this image. This is a transmission electron, an high-resolution transmission electron microscopy, so you can see the atoms inside the structure, and you can see that the five-fold symmetry is totally respected. Well, at this point, as you know, as Massimo told, the paper was sent to Science, and we got very, very positive and exciting reviews, and it was a very, very nice moment. Fortunately, some months later, the situation went very, very bad because as Danny had to fight a lot with the physical and chemical community for the skepticism encountered, well, we encountered something like this in the geological and geochemical community because our natural quasicrystal shows metallic aluminum inside. So a lot of person does not believe to the presence of metallic aluminum on the Earth because it needs too much reducing condition to form. So it is not possible to find. Even there are a lot of occurrences reporting metallic aluminum, so this consideration would be unnatural, man-made material, slag material. So we had to fight a lot to demonstrate that this is natural. How to do? We have only 3 millimeters of samples. Actually, probably in this period, it came 2 millimeters. Well, so the answer was this. Well, and the answer to help us in the naturalness problem was this grain was recovered in the same time copper grid Nan was analyzed in Princeton, and it is a 50 nanometer size grain, this one, and try to see why. Well, this grain shows only silicon and oxygen, and this kind of diffraction, this kind of electron diffraction. So in this kind of orientation, you can see something like a square, okay? Well, if you tilt it, you're able to obtain electron diffraction pattern for other orientations. Well, this is at the tetragonal unit cell we were able to find. Well, the fact to have only silicon and oxygen and this tetragonal unit cell unequivocally corresponds to the mineral stishovite. Stishovite is the high-pressure polymorph of silicon dioxide, it shows this kind of structure exhibits silicon in the octahedral coordination, so it is very high pressure. So this is the phase diagram. So you can see the stishovite is stable approximately at 10 GPa. So we are talking of 10 thousandths of atmosphere. It is not found on the Earth, but it is found only in particular meteorites, and it is found on the Earth only in impact craters. So very, very large meteorites hitting the Earth. So it was a very, very nice finding because it limited the case to different situations. What I have to show you, because it is an unpublished figure, so you can see that this is the stishovite grain. So it is an enormous blow-up of the stishovite grain. So this is 5 nanometers. And this is a blob, a metallic blob inside the stishovite. Well, so this is the silicon and oxygen only and the electron diffraction pattern of the light gray pars. And what about the metallic blobs? Well, it contains aluminum, copper, and iron. So it is a small quasicrystal embedded in stishovite, which testifies that also quasicrystal form at high pressure. Okay? Well, so something like a summary. There are a lot of geological information not useful for you. What do you mean that the sample was found in a remote region, and you know now, and the grains of quasicrystals are in contact with stishovite, the high-pressure polymorph. So what do you bet? It is terrestrial or extraterrestrial? Well, you know the answer, okay, of course, but it was very important because, fortunately, it is possible to distinguish terrestrial and extraterrestrial processes by using isotope measurements of light elements. Well, because stable isotopes in meteorites preserve some of the most dramatic evidence for the incomplete nature of missing of distinct presolar materials in the formation of the solar system. These are the light elements of isotope measurements that we have to do, and in which way you perform these kind of experiments with this kind of instruments. Secondary ion mass spectrometry, okay, SIMS. But of course, we have no large material, so we are very, very small, so we need nano SIMS. So it is ultra expensive to make something like this kind of measurements, and only few labs have this kind of equipment. Anyway, we were interested in the oxygen isotope measurements. Oxygen has 3 isotopes, 16, 17, and 18, and what we measured are the ratios between 16 and 17 and 18 respectively. Well, so when we carried out the isotope measurements on the internal material, so on the silicates attached to the quasicrystal inside the rock, and on the external material, so the whitish ring that we have seen in the resolution picture. How you can study this kind of isotope measurements? It is very easy. Here you have the ratios between 16 and 17 and 18, and you can see here 2 lines, TF and CCAM. TF means terrestrial fractionation. So each silicate you can find here in your garden. Yeah, so give a signal coming from this line or above. So all these are terrestrial minerals. This means carbonaceous, chondrites, anhydrous minerals. So each mineral is formed in a carbonaceous chondrites follow that line. Okay. So but it is perfectly matched because these are literature data. You can see that this kind of diagram works really. What about our data? Well, these are the silicates. These are our silicates. So you can see from this diagram, taken of different minerals, that our silicates, the silicates in contact with the quasicrystal, are surely extraterrestrial in origin. Okay? So the last thing, just the last 5 minutes, to show you what we have done in the last year. So the Florence sample was really, really small, as you know. So we tried to find out new samples because we would like to make a lot of new experiments. And so we tried to organize, actually Paul was the organizer of this expedition. So it lasted here approximately 40 days, and in an American style, this is the title of the mission, Finding a Needle in the High Stack at the Edge of the World. And so the edge of the world is really, well, these are the kind of animals we found out our tent. So there are a lot of bears, I promise you bears, and there are a lot of bears. But what is very, very dangerous, believe me, are the tons of mosquitoes that there are there. Really, really tons. So I don't know if you can see them. So I remember I can hear the zzz. So these are our vehicles. So there are something like modified snow cat. so to cross over the tundra. Yes. And so these are the pieces from the Anadyr, the capital of Chukotka, and these are the field plays. So we're approximately 350 kilometers to make across the tundra. So we are 4 days of snowcat. Okay, and finally some pictures of the field. So this is the son of Paul Steinert. This is Will, and he is a geologist at Harvard. And this is a wall of clay. So we are digging clay. And here are the first panning operation, because the clay is so sticky that we have to disgregate the third fraction in hot water. And the final moments are done with in a typical way to look for gold. So this is Valerie Kryachko. And finally, from 30 kilograms of clay, we obtain something like this. So an heavy concentrate where we look at in the field with a microscope to promising grain. Well, so just a slide of preliminary results, so just not for dissemination, and this is one of the grain we found there, and this is a typical extraterrestrial grain because this is something like a fusion crust, and this is a metallic grain which attracted our attention at the beginning because it was found the very first day, and so when I came back in Florence, I analyzed the grain, and pay attention, it gives the perfect five-fold symmetry, so it is the first single crystal of natural quasicrystal. And also, the chemical composition is exactly matching that we have already previously seen. This is the last image I want to show you, okay? This is one of the other grain found in the expedition. We have cut it and studied the internal structure at the scanning electron microscope. And this is something like a summary of what we have told today, because it is a chondrule. So if you show this image to a geologist, he immediately say that it is a meteorite because it is a chondrule, typical for carbonaceous chondrites, and it show, look at the red circle, a metallic grain inside, which is a copper aluminum. So it becomes obvious, everything I say today. Well, for the moment, the adventure stops here. Thank you very much for your attention. Yeah.